everybody. My name is John Thompson, and welcome back to another episode of Tesseract Talks. Today, we're going to stray outside our normal area and get into biology and molecular science, but of course, it's all going to be connected to AI. So I expect I'm going to be learning as much today as you are. So I'm very excited to have Mark Mackey with us, who's the Chief Science Officer of Cresset. Mark has been with the company for 24 years. Is that right, Mark?
That's correct.
Since the very beginning. So, Mark, do you want to give us a little bit of introduction to yourself and the company before we get into the questions?
Yeah, sure. Thanks, John. So I helped set up Cresset. This is nearly a quarter of a century ago. And our aim is to provide, in essence, tools to help our customers who are in the pharmaceutical industry discover drugs better. So we're not out there discovering drugs. We're sort of designing better shovels so that they can dig for gold, but we're not doing the digging ourselves.
Kind of like the old Levi's analogy,
Absolutely,
not the gold miners, but we're making shovels and
selling pans and things like that. But yeah, in essence, I'm not going to discover a cure for Alzheimer's, but if there's a cure for Alzheimer's out there, then the tools we're building will hopefully help find it faster.
Great. So there's an acronym that I actually had to look up myself, and we're going to use it a few times, ADME. So could you do us a favor and define that before we go any further?
Yeah, so drug discovery is a little bit everybody knows it's hard, but it's even harder than people think it is. So in general, what we're trying to do when we're trying to discover a new drug is to find a small molecule that you can put in a tablet that goes and interferes with the process in the body. Okay, and it usually does that by binding to a big protein molecule in the body. And so that's sort of the minimum thing you need to have in order to be a drug, is that your small molecule is going to go and it's going to bind to a particular protein in the body and make your headache go away, or make your cancer better, or fix the ache you have in your knees, or whatever it happens to be we're trying to cure. A lot of the hard part comes about trying to make sure that the molecule actually gets to the bit you're trying to fix. So you're going to take a tablet, then obviously the compound has to be stable, because otherwise it'll have gone off before you manage to get the tablet. It has to be sufficiently active that I can sort of fit a small amount of it in a tablet. And I'm not taking a tablet that's the size of a tablespoon, because that doesn't sell very well. And then it has to then get through the stomach, so it has to not fall apart immediately when hitting stomach acid. And then it has to be absorbed into the bloodstream. And then it has to be not chewed up by the liver, because that's what your liver's for, is for getting rid of compounds that your body doesn't think should be there. And then it needs to get to the right place in the body. And then it needs to get into the cells that it's trying to get into. And then it needs to interact with the protein and do its job. So there's a whole bunch of things that it needs to do. And a lot of those are actually quite difficult to predict, at least computationally. So ADME is absorption, distribution, metabolism, excretion. It's sort of a grab bag of all of those sort of non-functional requirements for your molecule. It's not about the curing cancer bit. It's about what does it actually have to do in order for me to be able to put a compound in a pill. And when you take that pill, it gets to the right part of the body and does what it's supposed to do.
Well, that's a great explanation. I have a much greater appreciation of the difficulty of getting drugs in the right place in the body. So thank you very much for that, Mark. So the first question is, what is fundamentally broken today in the ADME, and how ADME properties are predicted in drug discovery? What's Cresset actually doing to improve this?
So it's one of these sort of long-standing issues. As I mentioned, there's this huge grab bag list of properties that a molecule needs to have to go from interesting compound to actual drug. And ideally, the more of those properties we can predict ahead of time, then the greater the likelihood that we can discover a molecule quickly and not too expensively. So the field of sort of ADME modeling has been around for decades. The original models were done back in the 1980s and 1990s, back when I was starting out. There was quite a lot of modeling being done there. So there's an element where there's nothing fundamentally broken, but it's still very much an unsolved problem. Ideally, what we'd like to be able to do is to model everything on the computer, and you do an awful lot of computer modeling, and then the chemist in the lab has to make one molecule, and it's the compound that's going to go into the rats and into the people and become the drug. We're still a long way away from that. The average drug discovery project involves making hundreds or thousands of molecules, and each one is an attempt to solve all of the problems. So it's not so much what's fundamentally broken, it's more what are we still missing in order to maximize the value of our computer modeling. One of the things that has changed the game there is the advent of AI. Yeah, only in some cases and only for some people. And I'll sort of explain what I mean. So the issue is that a lot of the processes that we're trying to model for ADME properties are very difficult to do in a reductive sense because, does my compound get absorbed when it's going through the intestines, and does it get into the bloodstream? Well, that's quite a complicated process. There's lots of different cell types. There's lots of different transporters involved. It's hard to actually work out exactly what's going on for any given compound. So we're largely limited to more statistical. I've got a whole heap of compounds and I've managed to measure their absorption properties. And so can I build some sort of model that says, well, my compound looks more like the compounds that are absorbed well, and so it's probably going to be good. Or it looks more like the compounds that aren't absorbed well, it's probably going to be bad. And obviously to do that modeling well, you need a lot of data. And that's part of the hard bit because these are sort of complicated experiments and quite expensive to run. But then you need really good machine learning. And traditional machine learning methods, they've been around for a long time. They're pretty good at extracting a lot of information out. But especially once you start getting past a sort of critical mass of data, then the new sort of deep learning neural network methods really can squeeze a fair bit of extra information out of a data set. AIs are incredibly good pattern recognition machines. And so they can usually see something in the data that as people we can't, and as the more simple machine learning methods couldn't, and be able to make more accurate predictions of this compound really does look like it should be absorbed well, and this other compound really doesn't. And so if as a chemist I'm going to make one of them, make compound A, don't make compound B. And provided you can make that call accurately enough, you can really accelerate a drug discovery.
That's really interesting. Obviously, we've had AI around for about 70 years. We're coming up on the 70th anniversary of the 1956 Dartmouth Conference. It's taken us this long to realize what those fellows said back in the summer session that AI could be. So we're there, as you said. Machine learning, deep learning, generative AI has been taking up all the air in the room as of the last 3 years. Is there a generative AI component to what you guys are doing?
Well, we are doing generative AI. Generative AI can be quite interesting, but it doesn't help that much with ADME properties because, again, generative AI tends to be good at saying, hey, can I have some more compounds that look like this?
Yes,
and the hard part is defining the look like bit. So it's definitely of use. And once you've got good predictive models for ADME, then absolutely you feed that as inputs and you feed that as restraints into your generative chemistry. And that, if I'm training a generative chemist to try and produce me sort of drug-like molecules, then, definitely I wanted to pay attention to absorption and to clearance and to all the other ADME properties that we want. But it's more, the ADME stuff is more about sort of tweaking the objective functions. It's about telling it what sorts of things I want and what I don't want. And obviously, the more accurate your model's there, then the less you suffer from the old garbage in, garbage out problem.
Exactly. Your team is really modeling some very interesting reactions in the body and chemical reactions and different kind of binding. I was reading your website and it's a study. It's some really great information out there. So if anybody's interested in this area, definitely go to cresset.com and check it out. So when you're working on these ADME processes, drug discovery is a very complicated process. So how are you actually helping reduce risk and different costs that are in what could be a multi-year process?
So I think there's two aspects to that. One is just the pure cost saving in the better the predictions you have early on, the fewer compounds you have to make in order to find out that a good idea isn't such a good idea, right? So the chemists will be coming up with ideas that maybe we should tweak this part of the molecule and maybe we should tweak that part of the molecule. And some of those ideas will be great, some of them won't. It's a sufficiently complicated thing that as humans we can't usually tell. So traditionally drug discovery has been a little bit of a lottery. We can predict some properties, but for the rest, we just keep making molecules and hope that eventually we make one that's got the right combination of properties. And so it's interesting that even a fairly noisy and inaccurate model, provided there's some information content, it can actually speed up that process quite a lot. The model doesn't need to be accurate all the time. As long as it's better than a coin toss, then if you make the things that it says are good and don't make the things that it says are bad, you're going to get there faster than if, in essence, you're just guessing. And so, there's an element where the task we set ourselves isn't that hard. We need to be better than a coin toss. But because biology is complicated, even getting better than a coin toss can be quite difficult sometimes.
Agreed. Absolutely. There's lots of moving parts here. We've been talking about data science. We've been talking about chemistry. We're talking about AI as part of data science and chemical binding and different things like that. It's it, yeah, I'm sure to you at this point, it seems almost obvious how you bring all these elements together. But our audience has been hearing this subject for maybe 9, 10 minutes at this point. So how does Cresset bring all that together to do some of the things that you've already described?
So part of what we're trying to do is moving towards an industrialization of the drug discovery process. As I mentioned, largely, if you took a chemist from 30 years ago and dropped them into, they wouldn't recognize some of the lab equipment and they wouldn't recognize some of the modeling for things, but actually the entire process, there's a large degree to which it hasn't changed. I think the opportunity we have at the moment is to move things from the sort of hand-polished Rolls-Royce fenders that one guy took a year to make a fender of the car towards a more Model T. Let's put things on a pipeline and crank things out at speed, because that can actually make a lot of compounds that answer out the questions we want to be answered much faster. So I think there's a number of moves, especially in big pharma, to make the entire process a little bit more industrial at scale. And that obviously involves much more computer control over the things. So where rather than hand designing molecules, we're now got generative AI that's helping to design those molecules for us. Rather than having your individual chemists look at molecules and say, well, this could be good, and I'm not sure about its profile, and is it actually going to get what we want? We've now got a large swathe of machine learning models and AI models to help us get good predictions of those properties. And then increasingly, we're also getting robotic synthesis on the other end. The molecules can largely now, not necessarily completely, but to a large degree, the lab automation is much better than it was. And so the compounds are being made they may be made in large batches, they're being made on robots, and you're not looking at a chemist taking a week in the lab to make each individual compound. And the combination of putting all of those together should hopefully, in essence, reduce the cycle time and increase the amount of information we gain in each week of the drug discovery project. And that in the end translates to getting the compound into the clinic faster and getting it out there and helping patients faster, which is what we're all looking for.
Sure. Absolutely. I love your comparison of a Rolls Royce to a Model T. I did go to the Aston Martin factory a few years ago and help bolt the engine into a friend of mine's car, which was quite an experience watching them handcraft, true English automobiles. It was wonderful to see. All right, so let's move on to our final question. What separates the leaders in AI drug discovery than anyone else? And what kind of innovations do you see coming in the next few years?
So if you have a look around the life sciences and sort of search for AI in life sciences, there's a lot of hype. To these days, it's quite hard to get a biotech off the ground without saying you're going to use AI to solve the drug discovery program. And like all technologies, you need to be careful to separate the hype from the fact. So is AI useful? Absolutely. And we're very much at the forefront of helping to deliver AI and the value inherent in AI to our customers. But we also need to be careful about the claims that within 5 years, all drugs are going to be completely designed by AI with no human input. We're a long way away. So I think the leaders are going to be the companies that have intelligently looked at the pros and cons of different AI technologies, have worked out where they add value, have integrated that value into their workflows. So, in particular, one of the things that AI is really good at is automation, and in particular, sort of automating the simple stuff. And so,
yes.
10 years ago, if you want to take notes in a meeting, somebody has to take the notes and then manually summarize them. These days, Teams transcribes it and automatically provides me with an AI-generated summary. That hasn't necessarily added direct value. The AI notes aren't necessarily better than my notes, but it saved me a lot of time in every meeting. That's something I don't have to do. And I think it's those sorts of things, even in the drug discovery field. There's a lot of time savings to be made in taking the things that currently a lot of people have to sit in meetings and discuss ideas and work out what they're going to do and move information around. And that can all be automated using AI and AI agents in order to let people do what you really want them to do, which is to do the really deep thinking, which is where the AIs aren't quite there yet. And so I still think you need the people for the flashes of insight and the moments of inspiration. The more time you give them to do that, then the more value. And the other thing to just flag up is that at the moment, the statistic that people flag up is that 90% of drugs fail, which is true. And AI is not going to help with that statistic a huge amount, because the reason that most drugs fail is because we don't understand the biology well enough. And we had really got a hypothesis that there's this particular protein, and if your small molecule hits that protein, it'll make your headache go away. And eventually, after hundreds of millions of dollars of research, somebody makes a molecule to hit that protein, and it turns out that it does make your headache go away, but also makes your ears fall off, or has some sort of other bizarre side effect. And these things are usually just not foreseeable. Okay, so most drugs fail in the clinic either due to lack of efficacy. They hit the protein, but the protein doesn't do what we thought it did, or they do hit the protein and the protein does do what we thought it did, but it also does something else that we didn't know about, and that ends up causing side effects that make it unsuitable as a drug. AI is not really going to help with that in the short and medium term, because that basically comes down to the fact we don't understand at a low level, at a deep level, human biology well enough. But what we can do is, if we can accelerate the rest of the processes and automate the processes, and by bringing in machine learning models and generative chemistry models and things like that, make that process of getting a compound to test much more quickly and much more cheaply, then we can still reduce the overall cost. Even if we still have a high failure rate, provided those failures don't cost us nearly as much, then the overall process is still much more efficient than it used to be. And that, I think, is a worthwhile.
Absolutely. You made a good point earlier that AI in life sciences is everywhere. It's very difficult to tell who's actually making a difference. And you could actually take off the life science part. AI in almost anything at this point. You look at every website. Well, we saw last week, Allbirds is now not a shoe company. They're an AI data center company, which is
absolutely
mind-boggling in and of itself.
For people who want AI shoes, no doubt.
Yeah, exactly. I must thank you. This has been one of the most enjoyable Tesseract Talks sessions that I've held, and we have an ever-growing library of those. So thanks for coming on. Really appreciate your expertise and what you're doing for all of us in the world. This is a very important area, and we're excited to hear more about it. So thank you very much for being on the show. And I wanted to thank everybody. Thank you, everybody that watches these sessions and comes to the Tesseract Analytics website. We have an ever-growing library of Tesseract Talks sessions that we're recording almost every week. So drop by, on a daily basis, weekly basis, see who we're talking to. People like Mark here, who is very, very interesting and fun to talk to. So have a great day, everybody. Thanks for joining. Bye-bye.